System Design Fundamentals: Building Scalable Distributed Systems. Introduction: The building blocks of modern architecture. Understanding system design fundamentals is crucial for anyone building modern applications, whether you're developing web services, mobile backends, or complex distributed systems. These 12 core concepts form the foundation of scalable, reliable, and efficient system architecture. Today, we'll explore each fundamental component, understanding not just what they do, but how they work together to create robust systems that can handle millions of users and massive data loads. Scalability: growing beyond limits. The growth challenge. Scalability represents your system's ability to handle increased load by adding resources to the system. The diagram shows this concept with an expanding box and upward arrow symbolizing growth and expansion. Horizontal versus vertical scaling. There are two primary approaches to scalability. Vertical scaling, scale up, adding more power to existing machines, more CPU, RAM, or storage, and horizontal scaling, scale out, adding more machines to your pool of resources. Modern systems typically favor horizontal scaling because it's more cost-effective and provides better fault tolerance. Instead of buying one super powerful server, you distribute the load across many smaller servers. In real-world application, think of Netflix serving millions of users simultaneously. They can't rely on a single server, no matter how powerful. Instead, they use thousands of servers working together, each handling a portion of the total load. Load balancers, the traffic directors. Distributing the load. Load balancers act as intelligent traffic directors, distributing incoming requests across multiple servers to ensure no single server becomes overwhelmed. The diagram shows this as a central distribution point managing multiple server instances. Types of load balancing. Round robin. Requests are distributed sequentially across servers. Least connections. Requests go to the server with the fewest active connections. Weighted round robin. Servers with higher capacity receive more requests. IP hash. Requests from the same IP consistently go to the same server. Beyond simple distribution, modern load balancers also provide health checking, SSL termination, and can route requests based on content, geography, or other sophisticated rules. They're essential for achieving high availability and optimal performance. Object storage, scalable data repository. Modern storage solutions. Object storage represents a scalable approach to storing unstructured data like images, videos, documents, and backups. The diagram shows various data types represented by different shapes stored in a unified system. Key characteristics. Unlike traditional file systems, object storage provides massive scalability, can store virtually unlimited amounts of data, HTTP access, objects are accessed via REST APIs. Metadata rich, each object can have extensive metadata. Globally distributed, data can be replicated across geographic regions. Popular examples are Amazon S3, Google Cloud Storage, and Azure Blob Storage. These services handle everything from serving website images to storing enterprise backups and data lake storage. Message queues, asynchronous communication. Decoupling components. Message queues enable asynchronous communication between different parts of your system. The diagram shows this as a pipeline representing the flow of messages from producers to consumers. Key benefits. Reliability. Messages persist until successfully processed. Scalability. Handle traffic spikes by queuing requests. Fault tolerance. System continues operating even if components fail temporarily. Decoupling. Services can operate independently. Common patterns. Producer-consumer. One service produces messages, another consumes them. Pub-sub. Messages are published to topics and consumed by multiple subscribers. Request-response. Asynchronous request-response patterns for long-running operations. Microservices. Distributed architecture. Breaking down monoliths. Microservices architecture breaks applications into small, independent services that communicate over well-defined APIs. The diagram shows interconnected hexagonal services representing this distributed approach. Advantages. Independent deployment. Each service can be deployed separately. Technology diversity. Different services can use different technologies. Fault isolation. Failure in one service doesn't bring down the entire system. Team autonomy. Different teams can own different services. Challenges. While microservices offer many benefits, they also introduce complexity in terms of service discovery, communication, data consistency, and monitoring across distributed components. Caching. Performance acceleration. Speed through storage. Caching stores frequently accessed data in fast access storage to reduce latency and database load. The diagram shows this with the lightning bolt, symbolizing speed and quick access.
Caching levels: browser cache, client-side caching of static resources; CDN cache, geographic distribution of cached content; application cache, in-memory caching within applications; and database cache, caching query results and frequently accessed data. Cache strategies: cache aside, application manages cache explicitly; white through, data is written to cache and database simultaneously; white back, data is written to cache first, database later; refresh ahead, cache is refreshed before expiration. Database, data persistence foundation. Databases provide persistent, organized storage for your application's data. The diagram shows the traditional database representation with organized data storage. Database types: relational, SQL, structured data with relationships, MySQL, PostgreSQL. NoSQL document, semi-structured data like MongoDB, CouchDB. Key value, simple key value pairs like Redis or DynamoDB. Graph, relationship-focused data like Neo4j and Amazon Neptune. Time series, timestamp data like InfluxDB and TimescaleDB. Considerations: choosing the right database depends on your data structure, consistency requirements, scalability needs, and query patterns. CAP theorem, the fundamental trade-off. The impossible triangle. CAP theorem states that in a distributed system, you can only guarantee 2 out of 3 properties: consistency, availability, and partition tolerance. The diagram shows these as overlapping circles. Understanding the trade-offs. Consistency, all nodes see the data simultaneously. Availability, system continues to operate despite failures. Partition tolerance, system continues despite network failures. Real-world applications. CP systems. Banking systems prioritize consistency over availability. AP systems. Social media platforms prioritize availability over strict consistency. CA systems. Single node systems that don't handle network partitions. Rate limiting, controlling access. Protecting system resources. Rate limiting controls the number of requests a user can make within a specific time period. The diagram shows this as a funnel representing controlled flow. Common algorithms. Token bucket, tokens are added at a fixed rate, requests consume tokens. Leaky bucket, requests are processed at a steady rate. Fixed window, allow n requests per time window. Sliding window, more sophisticated time-based limiting. Implementation levels. Rate limiting can be implemented at various levels: API gateways, load balancers, individual services, or even databases. Partitioning, dividing for performance. Horizontal data distribution. Partitioning or sharding divides large datasets across multiple databases or servers. The diagram shows data split into distinct partitions. Partitioning strategies. Range partitioning, data divided by value ranges. Hash partitioning, data distributed using hash functions. Directory partitioning, lookup service determines data location. Vertical partitioning, different columns stored in different databases. Benefits and challenges. While partitioning improves performance and enables horizontal scaling, it introduces complexity in queries that span multiple partitions and maintaining data consistency. CDN, global content distribution. Bringing content closer. Content delivery networks distribute content across geographically dispersed servers to reduce latency. The diagram shows a global network with connection points representing worldwide distribution. How CDNs work. Edge servers, content cached at locations close to users. Origin servers, primary servers containing original content. Geographic routing, users automatically connected to nearest edge server. Cache invalidation, mechanisms to update cached content. Performance benefits. CDNs dramatically reduce load times, especially for static content like images, videos, CSS, and JavaScript files, while also reducing load on origin servers. Stream processing, real-time data handling. Processing data in motion rather than batch processing. The diagram shows data flowing through a processing pipeline. Key characteristics: low latency, process data as it arrives; continuous processing, handle unbounded data streams; event-driven, react to data events in real time; stateful processing, maintain state across streaming events. Use cases: real-time analytics, live dashboards and metrics, fraud detection, immediate analysis of transactions, IoT processing, sensor data processing, log processing, real-time log analysis and alerting. Popular frameworks: Apache Kafka, Apache Storm, Apache Flink, and cloud services like AWS Kinesis enable sophisticated stream processing applications. Integration: building cohesive systems. These 12 fundamentals don't exist in isolation. They work together to create robust, scalable systems. Example architecture flow: users make requests through a CDN, Load balancers distribute traffic across microservices. Rate limiting protects against abuse. Services use caching to improve performance. Message queues handle asynchronous processing. Stream processing handles real-time events. Partition databases store structured data. Object storage handles files and media. Everything scales horizontally for growth. Design considerations. When building systems, consider performance requirements. What latency and throughput do you need? Consistency needs. How important is data consistency versus availability? Scale expectations. How much growth do you anticipate? Fault tolerance. What level of reliability is required? Cost constraints. What's your budget for infrastructure? Team expertise. What technologies does your team know well? Conclusion. Mastering the fundamentals. Understanding these 12 system design fundamentals provide the foundation for building modern, scalable applications. Each concept addresses specific